Welcome. The purpose of this video is to show how to do analysis of a non-inverting op-amp circuit to determine the voltage gain of the circuit. This is about the simplest analysis of an op-amp circuit that we can do. It may look intimidating at first, but once you understand how it works, it's actually fairly easy. On the screen I've drawn the non-inverting op-amp circuit that we'll analyze. The triangular symbol is the op-amp. The resistors R sub 1 and R sub F provide feedback from the output of the op-amp to the input of the op-amp, and their values will determine the voltage gain of the circuit. In this analysis, we'll use the ideal op-amp model. This model is actually pretty accurate for many DC and low-frequency AC circuits. This model makes the following approximations to the op-amp. The first is that the current flowing into the non-inverting input is 0, and the current flowing into the inverting input is 0. So the idea here is we have infinite input impedance. The other assumption that we make is that the gain of the op-amp is essentially infinite. This approximation has some very interesting implications which I'll try to explain. So ignoring the feedback configuration, the resistors R sub 1 and R sub F for a minute, the output of the op-amp is the gain times the voltage at the non-inverting input minus the voltage at the inverting input. And this is going to be some finite number. Since this is essentially infinite, in real life it's very big, but it's not infinite, but we think about it as being very large, then in order for V0 to be some reasonable number, the difference between these two input terminal voltages has to be very small. And so the assumption that we will make is that the output, this point of the op-amp, will generate whatever voltage is necessary to make the difference between the input voltage for the non-inverting input and the input voltage for the inverting input. It will make the difference between these two essentially 0. So the assumption then will be that the not inverting input and the inverting input voltages are equal to each other. Now some of you may be thinking, well, how on earth can the output do whatever is necessary to make these two inputs equal? If you'll remember, hidden away inside this op-amp is a controlled voltage source, and this typically goes down to ground. And so basically what happens is the op-amp sets the output of this voltage source to be whatever it needs to be in order to make these two inputs equal. Now in real life this is constrained by the fact that real op-amps aren't just ideal voltage sources. They have limits in terms of how much current they can supply. They have limits in terms of maximum and minimum voltages. But again, for the ideal model, we'll think of it this way. We will work backwards in the sense that we will make the assumption that V plus is equal to V minus, and then work from here doing a Kirchhoff's current law at the inverting input to determine what this output voltage V out has to be. And again, in real life, sort of what happens is this output voltage will be whatever is necessary to make these two guys equal. So to do the analysis, we assume they're equal, and then we figure out what that output voltage would be. So hopefully that makes sense. So let's go ahead and do the analysis. Again, we identify V plus. This is the voltage of the non-inverting input with respect to ground, and V minus, the voltage of the inverting input with respect to ground. We will do a KCL, Kirchhoff's current law analysis, at the non-inverting input of the op-amp. You'll notice that the voltage of the non-inverting input with respect to ground, that is V plus, is equal to VI, the input voltage of our amplifier. We also know that V minus is the same as V plus from our ideal op-amp model, so V minus is the same as VI. From this node to ground, there is a voltage of VI. which then allows us to compute the current going through R1. So we'll call this I1. I1 is VI divided by R1. Okay. The current going into the inverting input is 0. That's part of the assumption of the ideal op-amp model. So that means that all of the current that goes through I1 has to come down out of the output of the op-amp and through RF. This is the same. The current through RF is the same as the current through R1. Okay, so if we know that, then we can compute the voltage across RF. So let's call this VF. This is equal to I1 times RF. We know what I1 is, so we can write this as VI times RF over R1. Okay, so we're almost done. The voltage across the output now, this V0, if you look at the way V0 is set up, it's the voltage across RF plus the voltage across R1. We know that the voltage across RF is VI RF over R1. That's basically this value. And we know that the voltage across R1 is VI. So now we can factor out a VI, and we get VI times 1 plus RF over R1. So there you have it. That basically gives us the output voltage of this non-inverting op-amp circuit in terms of RF and R1. So, for example, suppose that we have the following component values. Let's suppose that RF is 5K ohms, R1 is 1K ohm. Then we plug the values for RF and R1 into our formula for the gain, and we get that V out is 1 plus 5K ohms over 1K ohm. That's 5,000 divided by 1,000, which is 5. So the gain of the op-amp circuit is going to be 1 plus 5, which is 6. So that pretty much concludes the video. Again, the important concept, the way we get to this solution, is we assume that these two input voltages are equal and that the output VO will be whatever it has to be in order to make these two equal. So we assume that they're equal, then we work backwards to figure out what VO has to be. So hopefully this has made good sense. Thanks for watching.